Let's talk about geosynchronous satellites. Geosynchronous satellites maintain their orbit over the same place on the Earth at all times, somewhere over the equator. So what would the period of such a satellite be? The period would be 24 hours, which would be 24 times 60 times 60 seconds, which I think is 86,400 seconds. And I wrote here, see formula sheet. I actually already told you that the period of the Earth is actually 86,100 seconds. And I think I showed you Neil deGrasse Tyson talking about the difference between the days. And we realized the Earth actually rotates every 23 hours, 56 minutes, and something seconds. But if you use 24 hours, I'm not going to freak out, okay? But what we do then for a geosynchronous satellite is we let the period be exactly the same as the rotation of the Earth. And by doing that, it will appear to stay above the same point on the equator at all times, which is really handy because then it means that, for example, if you're a satellite dish back on Earth, you know that if you point at a certain area, your communication satellite is always going to stay right there. It's not moving around. How many of you have ever seen a satellite pass overhead at night? Okay. Those of you that haven't, well worth looking up at night. If you watch on a clear, starry night for 20 minutes, you'll see several satellites. They're pretty obvious. Oh, there's something that looks like a star. It's not. You're seeing the sunlight reflecting off of it, and it's moving. You can only see them, say, for a couple of hours after sunset or a couple of hours before sunrise. In the middle of the night, you can't see them because now they're completely in Earth's shadow. What you're really seeing is the sun poking over the horizon at them, reflecting off of it and bouncing back to you. So keep an eye out. You can get apps, free apps that will tell you which satellites are coming overhead. Well worth it if the International Space Station is coming overhead. It has been coming overhead right now, but we haven't had good weather for viewing. If we get to some nice weather, and I know the weather forecast is a nice, crisp, clear day, and it's going to be passing overhead, I'll let you know. It's neat to go and look at the International Space Station. What's B want us to find? Gravity is what's pulling us in a circle. Now, how did I know to do that? Because it does say the word orbit. It's going to be big G, big M, little m over r squared equals m. Which one am I going to use? Because period. Doesn't matter how big the satellite is. It's going to orbit at the same orbital radius if you want it to go around the Earth. We're going to use the 86,100 from our formula sheet because that's actually what it's going to do. You want it to rotate with the Earth. You don't want it to rotate with daylight. So we'll use the 8.6. I think it's 8.61 times 10 to the fourth is what it says on your formula sheet. Okay. Get the R by itself. I guess that. Oh, I remember. This is the cube root one because we're going to get the t squared there. We're going to get the 4 pi squared there. And then we said, how do we get rid of a cube root? I like this question. I like this question. Hey, it's nice. I'm forcing you to learn where your cube root button is if you didn't know already. So R is going to be the cube root of big G. Parker, what's big G? Not 9.8. What is it?
6.3. No. No. 6.67 times 10 to the negative 11.
And again, unfortunately, not a convenient number, but it's our universe. We're stuck with it. Big M is mass of the Earth. T squared is 86,100, or 8.61 times 10 to the fourth. It's less writing to write that in standard form. Don't forget the squared, all over 4 pi squared. I get, let's do this in one step, Mr. Dewick. Math cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th times 86,100 squared divided by bracket 4 pi squared. Let's check for typos. That looks good. That looks good. That looks good. Is that right? I think I made a mistake. That looks totally wonky to me.
I got that.
You got this? Is it 42152,615? Oh, okay. Spencer's wrong. 1, 2, 3, 4, 5, 6, 7. Oh, yeah, that's not too bad. 4.22 times 10 to the 1, 2, 3, 4, 5, 6, 7. It is. Don't forget the squared here. Okay. For what it's worth, that's the distance from the center of the Earth. That's the altitude above the Earth, and if you want it in kilometers, 35,000 kilometers, which is high. Lots of potential energy required to do that, but really useful because it's nice that then you have satellites where you know exactly where they are. Let me get the original answer back. Good morning, good morning. We're continuing from where we left off last day. He talked to me. It's called responsibility. This is what you have, yeah? Is it getting crowded up there? Because geosynchronous satellites are really useful. Are we going to run out of space if all of these countries are sending up a satellite that has to be at the same radius as all the other satellites? Well, how big is that circumference? The circumference is 2 pi r. If I go 2 times pi times that circle is really big. We got plenty of room to put more geosynchronous satellites up there and still have lots of room between them where we're not worried about them colliding. So there we're okay. Now let's talk about black holes. Example 3. I like example 3. I like example 3. Example 3 is a nice question. Suppose an 18,000 kilogram spaceship is orbiting a black hole with an orbital radius of 8.8 times 10 to the 9th meters. The black hole has a mass of 6.8 times 10 to the 32 kilograms. What's the gravitational field strength at this radius? I'm going to ask you to find a gravitational field strength, and you know what? For giggles, it's going to be near a black hole because I dream of a Star Trek universe where we can do this. The most common mistake, Nick, is kids go like this. Oh, gravitational field. They do that. That capital F, does that stand for field? That's force in newtons. But I will deliberately give you enough information that you can find that. And unfortunately, I'll give you 0. This will probably be worth 3 marks. I'll give you a 0. How do I find gravitational field strength? What's the symbol for gravitational? Little g, and I did give you an equation for little g. It's the force of gravity divided by the mass. And that's actually from Physics 11, because in Physics 11, whenever I said get the obvious one, you did that. So all I've done is I've said, we'll get little g by itself. But now that we're going cosmic, we can bring in the universal gravity force equation. We can bring in big G, big M, little m over r squared over little m. And what really happens is the little m's cancel. This is gravitational field strength. It's big G, big M over r squared. By the way, that's also technically an acceleration, because F equals ma, well, little m times a. Let's crunch this. Are you expecting something bigger than 9.8? Okay. Big G, 6.8 times 10 to the 32. This time the r is squared. 8.8 times 10 to the 9th squared. Do you get 586 units? You can say newtons per kilogram. You could technically say meters per second squared, because what that means is if you were to drop something, it's going to accelerate towards the black hole at the... Okay, don't clear your calculator. It's going to be a typo. Let me come look. I think I may have asked you this before, but it's a good repeat. Would this be fatal to those on board the spaceship? Why not?
Oh, because they're in orbit.
If they're in orbit, and do they actually feel the gravitational field strength right now?
Oh, wow.
Now, they'll feel it when they arrive to get in, although you can do that as kind of a free fall, or they'll really notice it as trying to get out. Because as soon as you stop free falling, you're going to start to notice it. But right there, it would not be fatal. Okay. Ooh, what's the escape velocity required to leave the black hole's gravity well from this location? It's going to be bigger than the Earth's, because it's a stronger gravitational field. How do we find escape velocity? Now, some of you may have memorized it, but just in case we haven't, let's derive it. It was first of all, is this saying how much work? No. And if we're trying to leave the astronomical body, are we in a stable orbit? No. So don't say gravity is pulling me in a circle. In fact, we're trying to change our height and change our speed. This is a conservation of energy. We said this, KE initial plus PE initial equals, but our argument was we wanted the final kinetic energy to be zero because we want to do this so perfectly that we come to a stop right when we've reached the edge of the universe. And since we're at the edge of the universe, the final potential energy is zero. Right? That was our argument. And so what we ended up with was a half mv escape squared plus negative big G, big M, little m over R initial equals zero. What did we do next? Yeah, you could cross out little m's. I'll do that on the next line. I think the next, I just don't like that plus that equals zero. I would make the first thing equal the second thing, especially with that negative there. We said, you know what? You can write this as a half little m v squared equals positive big G, big M, little m over R. And yeah, the little m's canceled. And Kessler, you're right. I think escape speed was 2 big G, big M over R square root. And, oh, wait a minute. Kiana, I have big G, big M over R squared. It seems to me if I just backspace, delete the squared, times by 2, and I know on my calculator, if I just type times 2, it assumes it's on the top if it's not in the brackets. Square root of that, that's my escape velocity. 3.21 times 10 to the 1, 2, 3, 4, 5, 6. Does anybody remember what Earth's escape velocity was? I think it was 11,200. So just for giggles, I'm going to divide this by 11,200. Roughly 300 times faster than the Earth's escape velocity, 287 times faster. This would be very difficult to do with our current level of technology. So probably in your lifetime, you're not going to see any missions where astronauts are orbiting black holes. But it'd be pretty cool. Also, Einstein showed us that strong gravitational fields also distort time in the same way moving really fast from special relativity distorted time. Strong gravitational fields slow time down at that location. So this would also give you significant time dilation. That's what the movie Interstellar was getting into. There's a scene where they leave one astronaut behind further from the black hole. They go down to the black hole for what for them is a few days or a few hours. And when they return, 20 years have gone by for their astronaut. He's already kind of old and gone a little almost crazy because he's been isolated for all that long. Yeah. Sorry? So, what would it be like to fall into a black hole? Let's put on our Sesame Street imagination. Let's suppose Owen is an astronaut and he's doing a spacewalk on this mission. And unfortunately, something goes wrong, your tether breaks, or if you're using a jetpack, it stops working. Or maybe you're just curious, and let's say that Owen is going feet first, falling into the black hole. What would happen? Well, as he got closer and closer and closer and closer to the black hole's event horizon, he would actually start to notice a little bit of a tug on his feet because the gravitational field would actually be stronger on your feet than on your head. As you got really close to the black hole, the gravitational field would be changing so fast, you would notice that your feet were getting tugged, almost like you were stretching. And at first, it would feel pretty good. I mean, we all like to stretch first thing in the morning, but very rapidly, it would be like the worst medieval torturer's rack where they stretch a body that you have ever seen. And in fact, as you continued to fall, eventually the difference in tug between the top of you and the bottom of you would be stronger than the molecular bonds that hold you together. You would bifurcate, probably right around your center. Right around your belly button, you would split in half. And as you continued, each of those pieces would further continue to bifurcate, would further continue to split in half. And so there would be 2 pieces, and then 4 pieces, and then 8 pieces, and 16, and 32, and 64, and 256. But not only that, as you got really, really close to the event horizon, the black hole's gravity would distort space-time itself. You would actually also be getting squeezed together. All of the molecules that make Owen up would be getting squeezed together like toothpaste being extruded through a toothpaste tube. And physicists have a name for that process. What do we call it? We call this spaghettification. That is what happens when you fall into a black hole. You split vertically many, many times, but you also get compressed longitudinally. And eventually, any particles that end up in the black hole, we think, my current understanding, because I haven't looked up Hawking radiation, we think it's lost to the universe forever. I think. Well, I heard of Hawking yeah, it's theoretical, not proven. Anyways, generally, stuff that ends up there is never coming out. It's lost forever. Example 4, a black hole has a mass of 7.2 times 10 to the 31 kilograms. Suppose a spaceship is that far from the center. What's the gravitational field strength? So I seem to recall gravitational field strength is that. Now again, if you can't remember, what we're really saying, it's the force of gravity divided by little m. It's the force of gravity divided by little m. And what happens? It's that. Or you can remember it this way. Little mg has to equal little mg. Whichever way you want to track this. But gravitational field strength universally is that. So let's crunch it. It's going to be big G 7.2 times 10 to the 31. Is the r squared this time, Spencer?
Yes.
Okay. And again, I'm also kind of doing this so you get practice typing these into your calculator, especially if you foolishly forgot your calculator last class and might want to practice on your calculator this class, not mentioning any names. But they might have rolled a 17 earlier. But also, the other reason I keep telling you to try these on your calculator, the faster I can get you, the more time you have to finish the test. And like, I don't want you to be so slow on your calculator that that's the defining factor here. I got no use for that. I got a gravitational field strength of 52.1.
Yeah.
It's about 5 Gs. Awkward, but survivable if you were. This one, you might be able to bring the astronauts in and get the astronauts out, especially if you maybe had some good harnesses or hammocks or cocoons or something that you could do to help them deal with those G loads on the way out. What's the escape velocity required to leave the black hole from this location? And again, you don't need to memorize that. I deliberately did not put it on your yellow formula sheet. I don't think I did I? No. You can derive it from conservation of energy, or you can have that in your back pocket. I don't care. Oh, the fact that I just found the gravitational field strength, it seems to me that if I just, for this one, is there a squared? Get rid of the squared, times by 2, and square root that. That's convenient. And I get 1.00 times 10 to the 6th. Liz, question? Is that Anna? Okay. At what radius from the center of the black hole does the event horizon begin? What's the event horizon? That's the magic spot where the escape velocity has to be bigger than the speed of light. Actually, the event horizon is the magic spot where the escape velocity is the speed of light. And any more than that, you need to go faster than light. So here's what we're going to do. We're going to start with our escape velocity equation. But we're going to let the speed be the speed of light. So v is going to become c. We're going to get the r by itself. What's the r inside of a big square root? What's the opposite of square rooting? And I'll get v squared equals 2 big G big M over r, not r squared. To get the r by itself, stuff moves diagonally. The r is going to end up there. The v squared ends up there. And which v am I going to put in? Speed of light, which is on your formula sheet. So it's going to be 2 big G. What was the mass of this black hole? 7.2 times 10 to the 31. Divided by the speed of light is 3 times 10 to the 8th. It's actually 2.9979, something close enough. Where does the event horizon begin? Do you get 3.2 times 10 to the 13? No, that's wrong.
Yeah.
I'm way off. What did I... Oh, I forgot the squared, Mr. Dewick. Here I'm yelling at Spencer. What's the most common mistake that kids make? Oh, shut up, Dewick. Practice what you preach. Right? It was v squared here, and I forgot to write it here. You get 107,000?
Yes.
106,720?
What else? Using 2 o'clock.
That's meters. Just for giggles, divide by 1,000.
Oh no, I did something wrong.
So you would have to take something bigger than the sun, a star larger than the sun, and if you could compress all of that mass so that it would fit on 2 of our football fields, because the radius is about a football field, so the diameter would be twice as big. Basically, if you could compress it so that that star would fit in our back field, that's now becoming a black hole. The density required is staggering. My brain can't wrap around it. Or sorry, that's kilometers. I said it's 100,000 meters. Sorry, 106 kilometers. That would be what? The distance from Vancouver to Hope-ish. So if you compressed a star into the distance from Vancouver to Hope, this particular star would become a black hole. So example 5, let's destroy the solar system again just for giggles, because I opened up with a thought puzzle about the sun becoming a black hole. Could it? No, there's other factors that determine whether as a star gets older, it becomes a black hole or a white dwarf or a red giant. There's various factors, and the sun will almost certainly become a red giant. But if it became a black hole, what would its radius be? Now, that radius is called the event horizon. Sorry, that point is called the event horizon. That radius has a fancy name. It's called the Schwarzschild radius, named after a German scientist who first wrote the paper on it. Yeah.
What is a red giant?
What is a red giant? So that's when a star did not have enough mass to collapse on itself to form a black hole. Right now, our sun is performing kind of a balancing act. Gravity wants to collapse it, but inside fusion is occurring, pushing outwards, and that's continuing on, and that'll continue on for a few billion years. There will come a point, and now it depends on how much mass the star has, so this is why various stars form various things. For the sun, there will come a point when the pull of gravity inwards is no longer to resist the push of fusion outwards, and it's going to get cooler, but fusion will essentially be able to get it to billow out. It'll become a red giant. Fusion will still be occurring, but it won't maintain its shape. That's a really simplified explanation. If anybody's watching on YouTube, you don't need to leave a note in the comments. I know what I said is technically wrong, but I'll give him a better explanation when I go find a good YouTube video that I trust that gives a good explanation. By the way, the Schwarzschild radius, that's actually the same as the event horizon. In other words, solve for r, let v equal c, the speed of light. Like we just did. So how small would the sun have to be a black hole? Well, let's get the r by itself. First, it's going to be v squared equals 2 big G, big M, big M over r. And then stuff moves diagonally. Don't forget the square this time, Mr. Dewick. The sun's Schwarzschild radius would be, what's the mass of the sun? That doesn't sound right to me. Times 10 to the what? Okay. I think stars have to have a mass of around 10 to the 32 before they can become a black hole. So the sun is about 100 times 2 less massive, however I would say that. all over 3 times 10 to the 8th squared. What's the sun's Schwarzschild radius? Oh! That's in meters. So about 3 kilometers. Smaller, significantly smaller than Pitt Meadows. Right? 3 kilometers is probably about from here to the theater mall on Harris Road there, the old theater. That's about 3K-ish. Probably a little more, actually.
I wrote the two and I typed in that space in between.
Can black holes be that small? Yeah.
Is it likely?
Put your pencils down, look up.